Thank you for coming. It's my pleasure to introduce Professor Shmuel Peleg from the Hebrew University in Israel. I've known his work almost since I started in computer vision way back in the middle of the 90s. And even today, when I'm going through the proceedings of a vision conference, I look to see if I can see some of his papers, because he has ideas that are really simple, very creative, and yield very impressive results, as you'll see in his talk today. So,
OK, thank you. So I'll discuss some work that we've done recently. And the main idea in the work is that time should not be chronological. So it's a funny notion of time. But before that, we see what can we work on. We want to be effective. So we want to use on very popular videos. So the question, what is the most common video? The question is not defined well. So ask, what's the most popular video camera? So we all know what's the most popular video camera. It's your cell phone. What the trouble is? The trouble is that no one uses it. It is in the pocket. It's rarely used as a camera. So then ask, what is the most actually video? What is the most video captured around us? And this is the most video captured around us. I'm sure you found some cameras around here. Each camera takes 24 hours a day, 7 days a week. Tons of video. There's no more video than captured by this camera. What's the trouble with this video? No one watches this video. So we see that kind of two deficiencies in two kind of very extreme, a lot of video, a lot of cameras that are not being used well. So first I'll see, can we make this video infinite, basically, that's infinite stream of video more usable? And also make some use of this very popular cameras around that are not being used well. Now, the real question is, what is the most popular video watched? Now, I don't know how to answer this. I'm sure that people around here, that Google at least, would know better to tell what is the most popular video watched. But I'm not going to address this here. OK. So let's look at these, what I call webcams. It's surveillance camera mounted somewhere looking. And these are just off the web. We record some. This is a camera in Stuttgart airport, and that's a camera, I don't know where, in some billiard club. Notice that there's no pockets here. You should ask to replace the table you have outside with a table with no pockets. It's more interesting. Anyway, so we have this video. We look at this video, and basically not much is happening there. Not much is happening. One person here. Why do you have so many tables? And airports usually are quite not very active when you look on the runway side. But still, the idea is, can we take this video and don't look at it to see what activity goes in Stuttgart airport or what activity goes in this billiard club? Do we really have to spend 24 hours to look for a full day, or do we have to spend 1 hour? And the answer is no. So we would like to do the following. We would like to answer queries like, show me in 1 minute the last 2 hours, or show me in 15 minutes the last 2 weeks. So basically, we have this system that will take this webcam and summarize for us what's going on there. And the way we do this is the following. We look at the video in three-dimensional space. So this is a picture, one frame in the video, and then we have a lot of frames. Right now, I'll address the issue of a finite video. So assume we have a video of a few seconds. So this video, a few seconds, is basically a three-dimensional volume. And in this volume, we have activities. And if we think that what's interesting is activities in video, usually activities are important, then we can shift activities from original time to a shorter volume. So activity that originally happened at a different time will now appear at the same time. So if each black snake like this represent what we call activity tube, we pack them into a shorter time. And in this shorter time, we show a shorter video with all activities. I'll skip how we compute them. to show an example, so this is a short video outside my office with a water dispenser. And we have 3 people coming, and the activity tube is like this. Someone is coming from the left is leaving, then another one coming from someone for the left, some for the right, and then another one for the left. So this is the video, the person coming from the left, the person coming from the right, sorry. Person coming from the left, person coming from the right, and then someone, let's see. Got slower. My computer is doing something in the background, I have no idea why. Let's see how we can revive the video. Just 1 minute. What happens here? Okay, so we see this activity. Now, it's a long video, so we have these 3 activities. We pack them in a shorter time, and we get basically, we see all 3 of them concurrently, like here in the shorter volume. So this is basically, we see all 3 together. We get much shorter video, and we see all people together. We didn't show a shorter video, and we do not miss activity. So what we see is this effect of different activities at different time. We pack them into a shorter time. What happens if there's one long activity happening all the time? So if this one long activity happening all the time, if we know what is the length of our output video, we can segment the output video into a segment and pack them into a shorter video. And this is the example. So we can have this video. This girl on the monkey bars is occupying the entire video. If you want to shorten the video by 1 to 1/3 of its length without losing content, we can basically show different periods of the girl that appeared originally at different time. We can show them simultaneously. So we get a shorter video without losing activity. It works also with a panning camera. If we take a camera, we pan, track this lioness. We summarize the motion of the camera by creating this mosaic, and the lioness itself showing 5 different segments at 5 different times concurrently. Okay. So what we like to do, we remember the webcam. We have a webcam. What we show now is a finite video. The webcam is infinite. It never starts, it never ends, it goes on infinitely. And what we do, we always, as the camera is recording, we analyze the video and we put moving objects aside, we list them in a database. When the database fills up, usually the video is infinite, our database is not infinite. Well, maybe this is not true in Google. People say to me that Google database is infinite. But at the university, it's not. We have to throw out object. The question is, how do we throw out object? That's another issue which I'd skip. And we got to bring the query service. The query says, show me the last day in 10 seconds, for example. So what I have to do first to collect all the activities that happened in the last day out of the database, pack them. And in the packing, I do not have to keep the original chronological order because the chronological order prevents me from using the time compactly, and then generate the output synopsis. So what will the 24 hours in 20 seconds of this airport? So this is the airport that's usually shown. Here is a summary, 24 hours in 20 seconds. So basically, I'll take objects from all different times and basically show them simultaneously. You see the airplanes and cars and things together. They didn't have together, but I pushed them from different times and show them together. There's one object which is a special object. I call the background. So the background object, it is there. I treat it separately. For the background object, I just do what's called time lapse. So I take one frame every a few seconds. So this is the airport, and this is the billiard club. So this is what I saw. I was wondering, is it only one table? Why do you need the entire club? So I came next morning and so show me the last night 10 hours in 10 seconds. And this is the last night in 10 seconds. So the idea is that once, if you have webcams, you don't only can see the boring activities that are shown on the left, but you can also see summaries of past time. People will be interesting. Let's go to a certain webcam and see what happened there. Assume there's a webcam out there looking at this area here or in this room. Most of the time it's boring, but maybe there's some activity in the last day. Okay. So, yeah.
How do you avoid overlap? Do you attempt to avoid overlap?
Overlap. When I pack, of course I can do overlap, but then the video will be incomprehensible because objects will be one on top of the other. On the other hand, I can assume I don't want any overlap. This will create inefficient summary. So there's a parameter say how much overlap I allow. In this case, for example, I allow, I think, 10% or 20% overlap. So for example, you have two buses that can go through each other because they each time, but they cannot sit on each other. So I do allow overlap because we know it's summary. No one can be confused that this is the real, any of these summaries is a real thing. So we know it's summary. All we need to do is to have enough or small enough overlap so we can distinguish object from one another and it be comprehensible. So there's a parameter that we can adjust. So the way of packing rather than, I'll skip this one. Okay, the one question is what is it good for? For us, it was good for fun. It's really, I think, fun. But there isn't any other usage for it other than fun. So I don't know. I imagine that we have, on the web, there's tens of thousands of webcams that you can see everywhere on Earth. I'm sure that when people will be aware that there's ability to put their camera on the web, more people will put their camera on the web. But the idea is how to provide access to these cameras. So maybe Google is a company that likes to collect all the information on Earth. This is one thing. You have Google Map. Every location you see a camera, you can see the camera live, but not only live, but you can also see the camera summarized over whatever period of time you wish to summarize. So maybe this can be one use of this synopsis. Other uses, of course, are for surveillance, security cameras, but that's not interesting applications. Okay. Remember time, we have a problem with time. We have a problem with time, especially when the time is chronological. Why do you have a problem? If, for example, you do mosaicing. Mosaicing is you have a camera, you scan the scene, and you stitch the images together. And here we have a trouble, because if we stitch them normally, we have, for example, we have wind in the trees here, and the wind is missing from the panorama. If we want to put the wind in the leaves, as it was originally, we have a problem. Because why do we have a problem? Because we have a shadow here of the branch on the top. We've seen the shadow in the original video 10 seconds before we see the branch, and now we see them concurrently. But they did not appear, we didn't see them concurrently, but now we want to show them concurrently. So what we do, we have to shift the object in time. And therefore, this is a similar object. The shifting in time is similar one to see in the synopsis. Objects do not appear in the original time. They appear in different time. So how do we do this? All the approach is based on first taking the video and making it, like I've seen before, making it into a volume, a three-dimensional volume called SpaceTime volume. To do this, we need to adjust the motion. We need to to do other things. We may talk about this later. And we create this space-time volume. And we create new images out of the space-time volume by running some surfaces through this. So we take a surface in this space-time volume. The surface cuts pixels in the space-time volume. And whatever pixel it cuts, this is a new image. If I want to create another image, I can do video frame after frame. I move the surface, it cuts new set of pixels. And so for example, if this was the orange line on the frame of original video, the black line on frame of the new video, and I progress as a new frame. There's basically each frame in the new video takes a collection of pixels. It cuts and creates a new image. So what kind of this stupid scheme can do? So this stupid thing can do the following. For example, take this video. That's a demolition of the Kingdom in Seattle, I think about 7, 8 years ago. Assume we did it for a movie, and we did the demolition, and then the director comes and says, we did a mistake. Actually, we wanted the center of the dome to collapse first and the sides later. And it happened that all collapsed at the same time. Or maybe we want the side to collapse first and the dome at the center later. We cannot do it again because the structure is not there. But we can play with time. How do we play with time? We take a surface. So this is the space-time volume looking from above. So we see each row is the top one top line in somewhere a cut here in the image. So we take a time front that a surface that the sides of the surface are in the past, and the center is in the future, and we run this through the space-time volume. So we get a sequence of images. Each frame generated, the center was taken from an image who is ahead of time than the sides. So all we need to do, we separate the shape of the time front, and we get a new video. In this new video, the center collapses first. If we want the side to collapse first, we create another surface, this surface, and we create this surface where the sides are from the past, for future, and the center from the past, and then the sides collapse first. So once you have this three-dimensional volume, very easy to recreate new things with different time ordering. Yes? Oh, of course. So when I say I'm cutting through the volume, I'm cutting a surface through a volume. So the surface goes in between pixels. So I must have. Excuse me?
Does it on or off the flow as it goes forward in time?
No. The surface just goes on what you see here. You just take the volume, it moves in the volume. We do interpolation. The interpolation due to the fact that the surface is continuous and the pixels are in discrete locations, so we need to interpolate. But we don't use optical flow here for this. We'll use optical flow interpolation for other things later. But
if you wanted this to happen really nice, then those slices would have optical flow between them, right?
well,
Talk about it later.
yeah, maybe. I don't understand that. There's sometimes you do need optical flow. You cannot do without it. But here we don't need optical flow. Well, let's do something more interesting. Racing. You know, there's this race. You want your kid to win, but he doesn't. What do? Well, no problem. The memory, you know, only the computer has the memory, so we can change the memory and do the following. Take the space-time volume, take initial image, original time. The last image, your kid is ahead of all the others. Your kid is ahead of all the others. You can interpolate kind of these times. So everyone is going in one speed. Your kid, his time goes faster. His times go faster, meaning that he's going to win. So he's now winning. Comes his best friend and say, hey, I want to win as well. Well, you can go take the same thing, go to his best friend, let him, his time run faster as well, and then he is winning. So, so everyone can show to his friends whatever video he watched. I I don't think there's any way to tell the original video from the remanufactured videos. Then come again trips. You're going on a trip. You see wonderful things. I've not been in Iguazu Falls. People tell me that's the magnificent falls, very wide. Everyone takes this type of way. They're so wide. This is the way you take it. Everyone takes a panorama of the falls. And of course, you can stitch them in the panorama, and you get this nice picture, but the water turns into ice. So water are frozen. So what we want to do, we want the water to fall as well. So we do this with the same space-time volume. We run the surface this way, and then we get both a panorama and the water is falling. And again, remember, there's a time shift here because we never saw these two parts flowing together. We showed them at different times. But the fact that this surface is diagonal basically turns time into space. And we show different things that appear at different times at different location. And this is another use. We said we look for use for cameras and cellular phones. This is an example of you see a scene, you take your camera, take a picture, and create this dynamic panorama. Of course, once we have this tool, every time I go to interesting places, I start taking panoramas. And this was in Saloniki. Again, you see this image from the camera, and this is the panorama that is dynamic of all the region. Okay, so this is a very stupid idea. It's not stupid, very simple idea. You take the video, organize it in a tube, and then run some kind of a slice through the tube and generate new videos. But it can generate something very non-intuitive thing. For example, if we take this is the space-time volume of the waterfall. So it goes from left to right. We see one frame after another. That's why it's diagonal, because the camera is scanning the scene. So as we progress the time, we go to the right. Now, look at this black time front. So time front, this is the surface we are running through this wall. We are running this surface. We'll move it down. So this is the intersection. And this is will be the output frame. We're moving down. We see what happened to the output frame. The output frame will move to the left. So basically, we got an input video that moved from left to right. And now we got an output video that go from right to left. Why should we do that? We have an input video that go from left to right. If you want an output video that go from right to left, what do we need to do? Just to play the frame backward, right? So we play the frame backward, and we have a video that go from right to left. But something is wrong there, right? The gravity is inverted. If we want to keep gravity, this is our method. In our method, this diagonal line, we get the camera going from right to left, but the water continues to go down. So we inverted the motion of the camera, but we did not invert the motion of the drops of water. So this thing, it's a very powerful tool, can be done by scanning this space-time volume. Now we look on cameras again, and we notice that when we have a camera, a location in the image means different ray in space. So if we take, say, a column in the center of the camera, we have ray in space that go perpendicular to the image surface. And if we take a column in the left side, we have rays going in different direction. So when we actually strip in the image, it means direction of rays. So how can we use that? So if you have a camera that is translating the word and is collecting a set of rays in all directions, if we just take a center column for every image and stitch it together, it means that we create what's called a push-boom panorama. We have arrays that are parallel horizontally. Vertically, they are perspective, but horizontally, they are parallel because they are all taken from the center of the translating camera. But if we, rather than stitching column from the center, we'll stitch column from the left side or from the right side, we get panoramas that also have parallel rays, but the parallel rays are tilted in different ways. So we see an object. One time we see an object from the left, from the center, or from the right. So if we go to our space-time volume presentation, this slice is stitching together of columns from the right side of the image. So this is one direction view of object. So when we move the slice, each time we take column from different location, each time we look at the object from different direction. So if we just view what we see, take this as the input video, for example. On the bottom, we see the slice in the right. We take the slice and move it from the right to the left and back. We get this effect. So we see that all we did was just taking the space-time volume and moving the slice from left to right. That's all. We can create views that represent three-dimensional images. And without actually computing three-dimensional image, we just kind of different slices of the space-time volume. Again, here, we build space-time volume. You see the camera is jumping on the helicopter, so we need to compute the motion. But after building the space-time volume, running the slice, we can see 3D. Something strange here? The camera isn't running. You notice it's standing. It's a derailed camera, actually. 2004, very strong earthquake derailed this Shinkansen. Think about sitting in a camera in a train at 270 kilometers, 270 miles. I don't know how much is the speed of Shinkansen, but something very fast. And then there is an earthquake, 9 on the Richter scale, and throw the train up and down, so it derails. But no one was hurt. Anyway, so off you go, trip. This is Caesarea in Israel. You take your camera, scan around, and not only you get the panorama, but you can get 3D of the thing. If you have a nice house, you can show it in 3D. Okay. So we've seen we have the space-time volume. We see that we can change order of event. We can look left, right. What happens if we take this surface, the plane that we take in the space-time volume, but rather than shift it left and right, we rotate it. So we take a column from the center of the image. This is one thing, but then we rotate it. So we try to take diagonal slice. So this slice starts from the left column, the left image, to the right column of the right image. What happens when we do that? One after we rotate it. So what happens is the following. So we have, again, I show you a camera that's translating left to right. Translating left to right. We look at the diagonal slice. So we take the left slice from the left image, and then the center slice from the center image, and the right slice from the right image. So basically, these are the rays that we'll be collecting from as the camera goes. The camera on the left looks at the left ray, the camera on the right looks at the right ray, etc. So if you collect them, we see rays that, in addition to the ray passing through the camera path, because all the rays were taken, all the images were taken from the camera going in a certain path, they intersect. All the planes intersect somewhere in a vertical line elsewhere. So basically, this creates a model of the camera called cross-lit camera. Cross-lit camera is a general camera, more general than pinhole camera, where the rays go both through a horizontal line and a vertical line at different location. So when the red and blue plane are glued together, this is a pinhole camera. But when they're taken apart, we call the cross-lit, which is a generalization of a pinhole camera. And basically, with mosaicing, we can play around with the location of the vertical slit. The horizontal slit, that's a camera path we cannot touch because it's a physical line generated by the camera. But the vertical line is a virtual line generated by the mosaicing, and we can play with it as we want. So we can kind of generate, for example, forward motion. If we change the angle of this slice, we can generate, change the location, and we move as if we move forward in the scene by rotating the slice. So if, for example, we take this horizontal video, this is one mosaic generated from the left side of the left image to the right side of the right image. And we take this and rotate this slice, And when we rotate, we move forward. And you can see that we move forward. You can see object hiding. It's not zooming. Objects are behind the table, are showing up. There's a lot of parallax. So as if we know the 3D of the object, as if we know the occlusion, but we don't. All we did was just rotating. That's part of image-based rendering, but it's a very simple image-based rendering because all we do was kind of rotating a plane in the space-time volume. We can have funny shape. I'll skip that. Okay. Now, assume that, I don't know if you've heard, but some companies are trying to mosaic streets, city streets, and show them on the web. This is an example of an attempt. This is my, my camera driving in a street in Jerusalem until the card was filled up. This is I don't know if you've done mosaicing before, but this is very difficult. It's very close object, very far object. The camera is unstabilized, jumping. It's difficult to do. Anyway, so we're trying to do a city block from this. No GPS, no laser range scan finder, nothing. Just a regular car and handheld camera locking this city block. Actually, it's no more the block. It's half a kilometer, so several blocks there. And indeed, wow, I didn't realize it's so long. Okay, so now if you thought about going to Jerusalem, you don't need to. You've been there, at least in one street. So this is a panorama that creates very, very long panorama of this half a kilometer. And I'll describe what we do in order to get this panorama or these panoramas and how can you avoid issues like distortions, etc. So first thing is, how do you, one thing, the first task here is to compute the motion of the camera. So we have a camera. The camera is moving, taking the pictures. And we cannot actually, the original mosaicing, as was traditionally done, is to compute the motion in the image. The trouble is computing the motion in the image is that, at least in our case, we have objects of many different distances. So far away object will move slower, close object will move faster. If we compute an image, we either compute the image of the motion of the far object or the motion of the nearby object. When they change, we get a change of motion, even though the camera did not change, but our motion computation changed. So there's a lot of trouble. So we need to do that. We need to compute the motion of the camera. A lot of ways to compute the motion of the camera. Nothing that we have tried work for thousands of frames without breaking. Most of them 10, 20, 100, and they break. And we want something that will never break. So we're looking for a method that will be reliable. Basically, what we use is two components that are working for tens of years and known to work very good. One is called two-dimensional Lucas-Canada motion, two-dimensional, not three-dimensional, and another one is stereo computation. So what we do an iterative process of compute the motion, two-dimensional motion, and then compute stereo and run back and forth. So most of our motion computation is in 2D, the good old reliable 2D methods. And then just do the diagram, and it shows that we do get very good, this is a measure of depth map. We use graph cuts to do this. This is the depth if you call each label is a constant distance. And this, if the labels are planes, they're more accurate. Actually, we thought that doing depth labels of planes would be complicated because the labels are complicated. But it seems that it's simpler because we have much fewer planes than in the constant. So we have fewer labels, so it's not fast. So it shows this is the depth example iteration. This is first iteration, second, third iteration. We see three iteration, everything, the motion and the depth are computed accurately in three iterations. And now, so what we have our camera, we computed the motion. So now we can go and walk around Jerusalem. So this is the cross-slit walking around, so we can just not only go left and right, but we can also get inside the side roads. So this is an example of getting inside the side. So we see, it's not zooming in, like we see the cars in front of the cars here. It's really kind of a three-dimensional walk in Jerusalem. We can take another sequence I took in a conference in Germany, create a mosaic, and this is sliding from left to right, just seeing different three-dimensional views. Would you call it a city street if it's a river street? Well, I guess it's hard to run your truck in the river, but a regular camera is easier to put in the river. We can also do a walk through left and right. And okay, one of the problems of making a very long mosaic, like in the city street, is distortion. Because when you do very long mosaicing, the problem is that the traditional mosaicing is push broom. And push broom have distortions that far away object will be very wide, narrow will be very, close object will be very narrow. A very nice work was done by some people in Stanford. Some of them are sitting here, here in this room. And it goes as follows. Let's take the scene, break it into parts, and let's design for each part a different cross-slit projection. Let's do a different cross-slit projection, and indeed it minimizes distortion, but there's one problem. First is it's not sure that the division into segments is optimal. It gets some minimal notation, but we are not sure that it's minimal. What we get, these are the cross-slit. We get alternating cross-slit between different areas. So this actually, when we look at the space-time volume, this is the kind of combination of cross-slit. It's slicing of the space-time volume, the one cross-slit, another cross-slit. So these different cross-slit that gives minimum distortion. So when we look at this, we figure out why do we need the curve to have discrete parts, each one having straight line. We can have a curve that be continuous curve with no distinguished parts. And basically, to find this general curve, which is not segmenting to parts, and which have a different, may have a different slope everywhere, much, much easier, because this can be done with dynamic programming. Optimization is trivial, and we get global optimization other than local. So this is much nicer. So what we do, we basically, if this is the sequence of images, we find this curve. We take strips for every image. Some part we get wide strip. We take wide strip, especially from parts that are different to stitch together. So rather than stitching together different parts, we just take a wide strip, and area that are easy to stitch together, we take narrow strip from them. Okay, the noise was from the outside. I thought that was a question. Okay, so one thing is how do we stitch a strip? One issue is if we have wide strips and the different depth will cause us a problem. This, for example, if we stitch strip, so this may be 10 feet, and the back is 100 feet from the camera. So just stitching strip causes both cutting object here and multiply object on the back. So instead of just stitching strip, we take a strip. The strip that we stitch in the panorama will be rectangle, but the strip in the image will be depth-based. So this is depth interpolation that we do here between the strip in the image and the strip in the mosaic. And so we discovered the cost of this curve that we want to run. So the cost first have distortion cost. So what is the cost of distortion? So the very way to define distortion, we found out probably the simplest cost was the variance of disparities of the pixel in a strip. So if a strip, the cost of the strip will be just the variance of depth. When there's many depth in a strip, the variance of depth is high, the strip will be high cost. If there is the strip, all the depth in the strip are uniform, like we see a wall of uniform depth, the strip will have low cost. So we can have many strips that low cost, few strip of high cost. So this is just distortion, but we don't need only to have minimal distortion. We need the image also to stitch right. So basically that you can stitch images and be continuous. And then the stitching means that if we have a strip, the right side of pixels in the image and the right side in the mosaic should be similar. So basically we have two elements of the cost, distortion cost and stitching cost. We create a graph that we represent the cost between the left column of a strip in image I and the left column in image T and the left column of J in image T. This is, build this graph. We find the path, optimal path using dynamic programming, and we get a mosaic. Now, these are just zooming in on some part using this push broom and the what we call MED mosaicing. MED is minimal aspect distortion mosaicing. So you can see in regular mosaicing, this is a car which is far away. You notice it's becoming very wide. The door is close. It's very narrow. You notice how can people walk in the door. And this is push broom. And MED mosaicing is in the bottom. You see both the camera, the car. Both the car is the right size and the door. There's no distortion or aspect distortion here. This is another view of push broom on top and MED mosaicing on the bottom. You see, this was also considered problematic areas because of moving people. When it's problematic, when we have a lot of different depth, we don't understand what happened there, we put wide strip. This is the width of the strip. So you can see this woman was taking complete strip. We took her. This woman, another complete strip. So we don't know when the difficulty there, we take wide strip. Wide strip, we mean a large area taken from a single image. When things are smooth, we can take a different strip from different areas. So this is the two mosaicing. This is just the path on top of the variance of disparity. We see that if this is, we bypass variances of disparity. And an interesting thing is here. We can see this is zooming out, seeing from a distance. This is a city block, one block. And we notice that we see two streets here and here. And each of them has its own projection. It's unrealistic projection. When we look over here, it may look strange. But when you look close and we walk, it looks very, very natural. You see this block on this side, we look from the left, we look from the center, and now we look from the right. So basically, this is a distorted picture of the block. We don't really see from one point of view the same block from the center, from the right, and from the left. But when we do this very long mosaic and we just walk along, we get a natural view. Every local point, we get a natural view. Only when we zoom out, we get this unnatural perspective images. So basically, here is the so this is the street, and basically we can take this half kilometer and walk along the street. You know, this company that has the city block view, did you try walking along the street? It jumps. So I hope that one day they have more smooth, so you can really glide along the street rather than jump along the street. I guess the data is there. So basically we can get a very long mosaic, and locally everything is the right aspect. And this was taken, no laser rangefinders, no GPS, nothing. Just a regular camera out of, looking out of a car of a window. And if one of the issues is to get the universe on the web, it takes a lot of time and a lot of tracks to get all the universe and to update it every time from the beginning. This way, everyone can take a video of his neighborhood, upload it to the web, and within 1 to 2 weeks, we can get all the universe mapped. OK, thank you.
So going back to the summary of the Stuttgart proposal, have you thought about using this method, say, as a compression method for video? Because you can compress a 24-hour video very efficiently, I think, using this.
Well, we don't, at least we don't guarantee that all the objects are there. So in our case, we know how many objects we've thrown out. We didn't show it, but I think that compression method eventually does it. When you use MPEG, what does MPEG do? MPEG compute motion for every object and background changes. So this compression be very crude compression. It'll be compression, but without all the object. So
Method you can do some queries on the compressor. I mean, you know what objects you have and where. And
well, it's not the compression. I have a database. What I showed you is basically a visualization database. The database is a list of objects. An object for me is a small page of the object a long time. So a list of objects where they are, some kind of feature on them, and the object themselves. So this, of course, is much smaller than the original video. And then we have the background. With the background, we take one frame every, say, minute, or a kind of time lapse of the background. So yes, there is a way to generate this, but I don't know if it's acceptable. See, what does the video? In video compression, you measure some kind of losses. And I guess for the measure used in video compression, you have tremendous losses here. But of course, you can take, from your object, you're going to reconstruct a new video from the object I have and from the time lapse of the background I have, and I can reconstruct something. It'll be different than originally. But actually, well, let's see. Let's think about it again. Usually now when people do compression, they take usually the mean square error of the difference. So now what we see here is that we don't have the mean square error, but we have all the object and all the activities. So maybe we have a different way of losing. So here we measure the error not by the mean square error, which may be meaningless, especially, for example, assume that you take you compare two different frame rate and resolution, everything. So maybe, but instead it'll be objects and activities. So maybe this is a different way to look at compression.
When you took a panorama and then used it to construct a approximate 3D scene and then zoomed in and out, there was a lot of distortion as you zoomed in and out. Wouldn't that be easy to eliminate?
Maybe. Well, the distortion is because the projection we do is cross-lit. It's not perspective. It's image-based rendering. We only have the horizontal translation. We don't have the vertical views, only the horizontal one. So what we can do is cross-lit. It means we can change the viewing direction of the rays left to right, but the way up and down, we cannot play with them because we don't have them. So this cross-lit, and it does have this distortion. And now the depth that we use is not, it's below here. It's, even though it's surprisingly more accurate than what we expected, it still is not very accurate. For example, there is this rail here. So let's say we get the general shape, but if, for example, we want to go around it to correct hidden areas, it's not accurate. So I don't think it's reasonable to expect that the 3D will be real 3D and we get a real model of all the scene and object and trees, and it's very difficult to get the real model of the world. So if we had real model, you're correct. We can move in and out, left and right. And some places are trying to build models. I think Google is trying to fit models to buildings in New York or something, I'm not sure. But if you have a real model, that's true. But the assumption is we don't have a model. So we use this depth only for computing the camera for stitching, but we don't use it to 3D model of the scene, so we can do real walkthrough in the 3D model.
So when you're zooming in and out, you're not using the depth?
No. We're using its image-based rendering. We use the depths only for the stitching, for the interpolation of the stitching. It's only for cosmetics, not for the essence of what we see. Okay, thank you very much.